This is part 1 of section 10.8, Power Series and Interval of Convergence. So this section connects what we've done with our infinite series with what we talked about in our last section, which was the Taylor polynomial approximations. So what we're going to do now is we are going to work towards, at the end, come up with Taylor and Maclaurin series of specific types of power series. Now what's great about power series is it allows us to see something infinite in terms of a polynomial. So that's why we went over a Taylor series, Maclaurin series, and our infinite series. So we can take very complicated functions and, for the most part, approximate them in such a way that they behave like polynomials, which are really well defined and easy to determine different properties of. So that's the whole goal behind especially power series. So let's start by the definition of a power series. So a power series, if you have x as a variable, then we have an infinite series of this form. So we have a coefficient or a leading coefficient a sub n, x to the n, that can be written out in terms of a polynomial, the general form of a polynomial. So this is called a power series. And while an infinite series of the form, and then we have the summation from n equals 0 to infinity of a sub n times x minus c to the n, is a power series centered at some point other than 0. So the first part was a power series centered at 0, and the second one is a power series centered at c, and of course c is a constant. And then to relate that to what we did in our last section, Taylor polynomials centered at c have this form. F of x is approximately equal to p sub n of x, which is our Taylor polynomial. So example 1 is going to have some important details to consider. Now, what you want to remember is some functions will not generate a Taylor polynomial at x equals c because the function itself or one of its derivatives does not exist at c. So you have to make sure that you think about that before you try to write a Taylor polynomial or a power series. So that's what this example is about, and that's what we're going to go through. So if you look at letter A, what you have is y equals the square root of x minus 1 centered at 2. And the answer to this is going to be yes. We can write a Taylor polynomial here because the domain is 1 to infinity. And so 2 does fall in that domain, so we are fine. Now the next one is y equals the natural log of x minus 1 centered at 1. And so for this one, the answer is going to be no, because at x equals 1, we're not going to be in the domain. We're going to end up with ln of 0, which is undefined. So if we want a Taylor polynomial for y equals ln of x minus 1, we're going to have to make sure we center it on a point that is in its domain. So it'd have to be greater than 1. So the next one is y equals cotangent x centered at 0. And again, the answer is going to be no, because x equals 0 is not in the domain. Of cotangent of x. Now think about it. If you're not sure about that one, remember cotangent is x over y, or cosine over sine. So at 0, you would have 1 over 0, so that is undefined. Letter D is going to be no again, because at -1, if we take, it looks like, so you can look at the function and go, okay, so I'm going to have square root of 0, that's fine. But if you take the derivative, you're going to have 1 over 2 times the square root of x plus 1. And so this is going to be undefined at -1. So this is no, because the y prime not defined at x equals -1. Okay, so you guys try the next two and see what you get for those, and then I will share the answers with you. So there are the answers for E and F. Hopefully you got those answers. If you didn't, you can always ask me and I can explain them to you. Okay, so you want to make sure that you're thinking about that before you start creating a Taylor polynomial or a power series. Okay, so now there are two things that we need to consider once we got past the point that we are going to create this Taylor polynomial or power series. First, we've seen that except for geometric and telescoping series, you can't sum most series with an infinite number of terms. And also not all Taylor series will converge at x. But we will show how an infinite Taylor series will be exactly equal to their parent functions for x values that converge. And we'll get to that later. So let's just talk about where we're going to have some problems, and we'll get into that. So example 2. So given f of x equals the natural log of x, construct a Taylor polynomial of degree 4 centered at x equals 1. And this is one of the classic examples for a Taylor polynomial as the natural log function. So I'm going to go ahead and write out my derivatives here and evaluate it at my center, which is 1. Okay, so we know this is ln of x. I'm just trying to be. And then we're going to have 1 over x, and then minus 1 over x squared. The next derivative is going to be 2 over x to the third. And then finally, the last derivative is going to be -6 over x to the fourth. And now if I evaluate these at 1, so f of 1 is going to be 0, f prime of 1 is going to be 1, f double prime of 1 is going to be -1, f triple prime of 1 is going to be 2, and then finally the fourth derivative at 1 is going to be -6. Okay, so then what we can do is write our Taylor polynomial. So P4 of x is going to equal x minus 1 with the 1 factorial, but that's 1, minus, and then we're going to have x minus 1 squared over 2 factorial, and then we're going to have plus, because we have a positive 2, times x minus 1 to the third over 3 factorial, and then we're going to have minus 6 times x minus 1 to the fourth over 4 factorial. So there's our Taylor polynomial. If you want to write out the factorials, you can. And so I'll write that here. It's actually in the picture of the graph I have there. But if I simplify this, I get x minus 1 minus x minus 1 squared over 2 plus 3 factorial is 6. So then I have x minus 1 to the third over 3, and then minus 4 factorial is 24, so then I have x minus 1 to the fourth over 4. That's why natural log makes such a nice Taylor polynomial, because it's form when you write it out. Okay, so it says if you use your calculator to compare the original function to your approximation, what do you notice? And what you're supposed to notice is in this area here, where we're doing our 4th degree polynomial, is that it's very close to the function itself. So near x equals 1, the Taylor polynomial and the function are nearly identical. And we talked about in the last lesson too that this is where we get our linear approximation idea as well, is we're just creating a very limited term Taylor polynomial, just, like a first degree. So because we're making a linear approximation, and that's why we say it only works near the value that we're looking for it. Okay, so we're supposed to write out the general terms of the series and then put it in sigma notation. So we have our polynomial. I'll just rewrite it here again so we have it since I covered it up. So P4 of x is our x minus 1, and then we have minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 to the 4th over 4. So what we can see is we're going to have an alternating series, and we have our x minus 1 term that's going to be to the n power, and then we're going to have an n in the denominator, because this is our first term, second, third, and fourth. So these are where our n's are. So we're going to have the summation of n equals 1 to infinity of our negative 1. Now we want our first term to be positive, so let's just add a 1 to this. So we have to the n power plus 1, so that our odd terms are the ones that are positive and the even terms are negative. And then of course we have our x minus 1 term, and that's going to be to the n power, and then we're dividing by n. So there is our power series. Okay, so part D, substitute x equals 2 and apply your convergence test. So if we let x equals 2, this is going to give us this series. So we're going to have our negative 1 to the n plus 1, and then we are just going to have 1 to the n, which is just 1 over n. So simplifying this, it's just going to be our alternating harmonic series, which we know converges. But let me just go through that. So that's a good review right now. So what we have then is, our first thing is to notice that a sub n is equal to 1 over n, and that a sub n plus 1 is going to be less than a sub n. So then our second thing is that as our n's get larger, that we have a positive a sub n. And then finally, when we take the limit as n approaches infinity of a sub n, we're going to get 0. So therefore, by the alternating series test, helps if I could spell the word test, alternating series test, the series converges. Okay, so a little fact about pi. We only need 39 digits of pi to calculate the circumference of the observable universe to within the width of a hydrogen atom. So if you think about what you did in chemistry and how small a hydrogen atom is, and if you think about you only need 39 digits of pi and that you're within our observable universe, that's pretty amazing. So we're doing this because polynomials are much easier to work with than transcendental functions. So often an accurate approximation is just as good as an exact value. So in the next part of this video, we're going to talk about when does a power series converge, and we have lots of tests for that. That's what we've been working on. And then finally, if they do converge, they may not converge everywhere. So how do we determine that? So the nice thing is we're going to use the ratio test for most of them, and we're going to talk about the radius and interval of convergence. So that's what our next video is going to be about.